The two types of body armor are hard body armor, which is made of stiff and heavy inflexible ceramic plates, and soft body armor, which is essentially a simple ballistic vest which, while more flexible, has comparatively less ballistic resistance and as such is susceptible to blunt force trauma. The inspiration of our project comes from the telson of the peacock mantis stream that can withstand many massive blows from club-like appendages from other streams during interspecific competition. Our main purpose of this project is to improve the ballistic properties of our armor by reducing stresses and displacements at impact point and overall structure to prevent bottoming out and total structural failure. We begin our experiment by first taking the telson of a real peacock mantis stream and taking a 3D scan of it so that we analyze its structure in greater detail. After this, we created a simplified model based on what we saw in the 3D scans using SolidWorks. The models were given a central column 12 mm wide, and this was done for two primary reasons. First, is that during the physical experimentation, the presence of a central column will also increase the probability of the projectile impacting the model at the desired location. Secondly, due to limitations of the software, a remote load can only be applied on the plane, thus the need for a flat center column. A constant remote load mass was then applied on a circle with a diameter of 12 mm in the middle of the central column. 5 series of simulations were carried out with the optimal structures of each simulation series progressively improved. For the first simulation series, we compared the ballistic properties of common load-bearing structures, the mantis stream, and a normal, which in this case is a flat plane. Our objective in doing this is to compare the effectiveness of stream model as compared to other possible structures already commonplace. In the second simulation series, we then changed the angles of the carinae of the mantis stream. We were looking to find the optimal angle at which the stream possessed the best ballistic properties. In the third simulation series, we varied the scale of the model to attempt to achieve the optimal scale for the model. While the dimensional components were scaled, we kept the width of the central column at 12 mm to keep the area that remote load is applied to constant. In the fourth simulation series, we altered the thickness of the intercarina zones in order to replicate calcification present in the original scan model of the mantis stream. We limited the maximum number of thickened zones to 2 out of 4 since models with more than 2 zones thickened might as well have the additional thickness placed across the entire structure. At this juncture, we observed that the majority of the stress present was on the carinae. Therefore, for the final simulation, we proposed to replace the point carinae with a ridge instead to allow for increased flex to absorb more stress. As such, our final model was a derivative of the mantis stream with a carinae angle of 60 degrees, scale of 64 degrees, increased thickness in zones 1 and 3, and all its carinae replaced with ridges. Our objective for the physical testing portion was to confirm that the models exhibit progressive improvements as the simulations progress. We printed all the 5 shortlisted models using a 3D printer and folded Kevlar around the model using the vacuum-assisted liquid transfer method. We then impacted the models with ball bearings of 12 mm and roughly 7 grams in mass using a gas gun. We kept the velocity of the ball bearing at a relatively slower speed of 13 meters per second to allow the ball bearing to bounce off yet not penetrate the Kevlar model. The velocity of the ball before and after was recorded and the coefficient of restitution, impulse, and loss of energy was calculated. The physical impact testing confirmed that the final model from the simulations exhibited superior ballistic properties with a lower coefficient of restitution and higher energy absorption. The ballistic strength of the mantis stream structure derivative can be attributed to its unique geometry, which is composed of both stiff and flexible subsections which may culminate in flexible fault lines which collapse and absorb significant energy during impact, while stiffer subsections do not buckle down as much, resulting in the structure retaining its shape. This results in the structure achieving a particular dome-like shape during impact and retaining its original shape immediately after the removal of contact of the projectile. Simulated static load tests show that the greatest performance increases from simulation 2 to simulation 3 where the specific zone's thickness of the structure was altered. This was caused by how the thickened zones increased the partial stiffness of the model, which helped shape retention while maintaining energy absorbability. Physical ballistic testing showed that the trends of impulse resulting from the impacts oscillate slightly, indicating changes in stiffness through the different stages of development. Progressive improvement to the model through the 5 simulations most likely resulted in the exhibition of the combination of stiffness and flexibility, causing superior performance.